In this video, we're going to explore the logic of confidence intervals, and we're going to do that by looking at one sort of major example and get the sense for why we would want to even construct a confidence interval in the first place. So the example is this: what proportion of U.S. adults watch a certain TV show? That's a question that many people would like to know the answer to for any given TV show. The people who are making the show want to know how popular it is. The network that's showing it want to know how many people are watching it. And then the companies that are advertising during that show want to know how many people are watching it because they want to know whether it's worth their money to advertise it. So this proportion exists. So let's call it P. It exists. We'll call this proportion P. How can we estimate P? How can we estimate that proportion? We cannot, and it's not feasible to, we're not going to ask every adult in the United States whether or not they watch this TV show. It'll be a simple yes or no question, but we're not going to because it's not feasible to ask every U.S. adult. So one way that we could estimate it would be to take a sample. And find the proportion of that sample. Okay, so let's suppose that we've done that. A sample of 100 U.S. adults finds that 25% of them watch this TV show. That 25% represents a value that we'll call P hat. And that is equal to 0.25 here. P hat is the value from our sample, so it is a statistic, as opposed to P, which was the parameter. So how likely is it that P hat is the same as P? Is it likely that 25% is the proportion of all U.S. adults who watch the TV show? No, not likely that that's going to be the case. Maybe it's close to 25. But how likely is it that it's exactly 25? Very, very low. So could we get a better estimate? Sure. One way to get a better estimate would be maybe take a larger sample. But if our 100 U.S. adults is representative of the population as a whole, or pretty well representative of the U.S. adult population, we've chosen our sample well with randomization, then we may not need a larger sample. What we could do is we could take more samples of the same size. Instead of taking a larger sample, let's just take more samples of 100. Well, if we did that, we could plot all of those. They would all yield, each one yields a P hat. It yields a proportion, a statistic of the proportion of people in that sample who watched that TV show. So if I do lots and lots of samples, I can take each of those P hat values and I can plot them. And that forms the sampling distribution of P hat. So I have a picture there of what it might look like. It has some mean, some mu of P hat. And it has some standard deviation, some sigma of P hat. Now I chose to draw it in the way that I did. I chose to draw it so that it looks like a normal distribution. Well, how do I know that it's going to look normal? That is what the central limit theorem tells us. The central limit theorem, or the CLT, says that as long as my sample is at least 30, the sampling distribution of the sample statistic, which in this case is a proportion, should look approximately normal. What is mu of P hat? What is the average? What is the mean of P hat? Well, mu of P hat is going to be P. It's going to be the true value. That also comes from the central limit theorem. That's going to be the parameter. So if I take lots and lots of samples, all of us the same size, so in this case all of size 100, and I find the proportion from each one of those samples, so I take all of those statistics and I plot them as a dot plot and I trace it out into a curve, it's going to look normal or approximately normal, where the center of it, the mean of it, the average, is the true value for the population, is the parameter. Because if I take samples, I'm going to get some that are close to it and some that are a little further away, but more often than not, I'm going to be close to the actual value. So the center of this distribution is going to be the actual parameter. What is the standard deviation of p hat? Well, we have a formula for that. Standard deviation of p hat is the square root of pq over n. Remember, q is 1 minus p. Somewhere on this curve, somewhere in the sampling distribution of p hat, lies the specific p hat of 0.25 that we obtained from the one sample that we took. How close is p hat of 0.25 to p? Remember, p is the center of this. P is that mean. How close is 0.25 to that? Is it above it? Is it below it? And the second question, why do I care how close it is? Well, I do care. I care a lot because I'm not going to take lots and lots of samples to obtain lots and lots of values for p hat. And I'm not going to take those values for p hat and plot them and find their mean, because that's cumbersome and that's expensive in the real world. Instead, I'm just using my one sample with my one p hat of 0.25. My one sample of 100 people with my one p hat that I got from that sample of 0.25. So I do care how close it is. And question number one of how close it is really the best question that I can ask, because I'm only taking this one sample. So being able to tell or get a measure or get a sense of how close that is to p is very important, because I just have that one sample. And that's what I'm going to use to estimate what p is. So it would be great to have an understanding of how close 0.25 actually is to p. So how do I answer that question? Well, maybe by asking myself this question: how close do I want to be? How close do I want 0.25 to be to p? In other words, how confident do I want to be with my results? Let's say I want to be 95% confident. That means that if I were to take all possible samples of size n equal to 100, 95% of them would be close enough to the true p. That's what it means to be 95% confident. If I take lots and lots of samples, all the same size, so all in this case the size of 100, 95% of those samples will yield a p hat that's close enough to p. So how close is close enough? This value of how close it is called the margin of error. There is some margin of error, and often when you hear polls reported in the news or in the newspaper, they'll include the margin of error, but they never explain what it means. We use that margin of error to calculate the confidence interval. The confidence interval is the statistic. So in this case, the statistic is that p hat that we got, which is 0.25, and we're going to add and subtract from 0.25 the margin of error. The confidence interval is literally an interval. It's a set of numbers centered at the statistic, centered at the p hat. So this picture tries to give us a sense of how confidence intervals work. There is some true value. There is some p, which I've marked in gray there. P lies somewhere along the number line from 0 to 100. It's a proportion. It's a percentage. So somewhere on that number line is p, and I don't know where it is. What I do know is the p hat that I get from my sample. Let's say I take a sample, and I've got the p hat, which I've marked p hat 1 from that sample. Then I take my confidence interval, which is a set of numbers above and below my p hat 1, my p1 hat. It could be that that confidence interval includes p, as it does in that first example there. It could be, as it does in the second one, that it doesn't include p. That my interval, it could be that the p hat I get from my sample is too big, that even when I take my interval, it still doesn't capture p. It could be that the p hat and the interval formed by p hat does capture p, but just barely. Or it could be that I'm completely away from it and I don't capture p. So it could be above P, it could be below P, we don't know. And it could be that the interval captures P, it could be that it doesn't. So how do we calculate that margin of error? The margin of error is the critical value times the standard deviation of the statistic. The critical value times the standard deviation of the statistic. So the confidence interval then, which we said was the statistic plus or minus the margin of error, so the interval centered at the statistic with the same gap to the left and to the right of it, which is our margin of error. So we go the same distance to the left and to the right of our statistic. That forms our interval. These are open intervals, if you're interested in knowing that. That is the same thing as taking the statistic plus or minus the critical value times the standard deviation of the statistic, because that's what the margin of error is. Well, the standard deviation of the statistic, this is equal to what we just had before, the square root of PQ over N. The problem is, if I don't know what P is, how am I going to calculate that? I can't, because that requires knowing P, and Q comes from P. So I can't calculate the standard deviation of the statistic because I don't know what P is. That's the whole point. So what I do, the best thing I can do, is estimate that P with the P hat that I got, the statistic that I got from my sample. So this is approximately equal to the statistic plus or minus the critical value times what's called the standard error. The standard error is the square root of P hat Q hat over N, where Q hat is 1 minus P hat. This I can calculate because I have P hat. Now this is an estimate of the standard deviation of the statistic. And it's a good enough estimate. It's close enough. This is close enough if I satisfy the 10% condition. And the 10% condition says the size of the population, which we call capital N, is at least 10 times the size of my sample, or my sample is smaller than 10% of the population. Now I have 100 people in my sample. Certainly there's more than 1,000 people in the U.S. population, so I satisfy the 10% condition here easily. So then I can estimate square root of PQ over N with the square root of P hat Q hat over N. So that's how we form the confidence interval. In general, in any specific instance and any type of confidence interval we're forming, that formula is the same. Not the square root part, but the statistic plus or minus the critical value times the standard error is always what we're going to do. How we calculate the standard error and how we calculate the critical value and what the statistic is will be different for every confidence interval we make. But specifically, for the 95% confidence interval of the true proportion of U.S. adults who watch the TV show, we calculate the confidence interval as our statistic, which is our P hat, plus or minus the critical value, which for proportions is a Z value, what we call Z star, times the standard error, which is the square root of P hat Q hat over N. So again, this forms an interval where P hat's at the middle, and we're adding and subtracting. So that's what the plus or minus indicates, the same amount from that P hat. So we get an interval around P hat, where P hat's in the middle. Okay, well, let's fill this out. P hat is 0.25. 0.25 plus or minus Z star, which is 1.96, and I'll explain where that comes from in a moment, times the square root of P hat, 0.25, times Q hat, which is 1 minus 0.25, or 0.75, over N, where N is the size of the sample, and that was 100. Now, where does the 1.96 come from? If we think of the normal distribution, saying that I want to be 95% confident means that I want 95% in the middle of the normal distribution, centered around P, the true parameter, the true proportion. If there's 95% in the middle, it's 100% total, right? So there's 5% that's not in the middle, and that's divided evenly to the left and to the right of my 95%. So there's 2.5% down here and 2.5% up here. So if I do in my calculator inverse norm, and when I obtain this value right here, that's my z star value. The way I obtain that with inverse norm is to put the percentage that's below that value. Well, that would be 97.5%. I put inverse norm of 0.975 into my calculator. If it asks for you for a mean and a standard deviation, put a mean of 0 and a standard deviation of 1, because this is a standardized value, a z-score. Then I get, my calculator tells me 1.96. So z star, which gives me 95% in the middle, is 1.96. So that's where that number comes from. If you were asked for any other percentage, set it up like that, with that percentage in the middle, figure out what's below and what's above, and use inverse norm. Okay, so I can work this out. The square root part works out to be 0.0433. So I've got 0.25 plus or minus 1.96 times 0.0433, which is 0.08487 approximately. So if I take 0.25 and I add 0.08487, that'll give me the upper value of my interval. If I take 0.25 minus 0.08487, it'll give me the lower value of my interval. Those two values are 0.165 and 0.335. So that is my interval. Notice I've written it as an interval, an open interval. So it's the numbers from 0.165 to 0.335. Notice the center of that is at 0.25. We've gone the same distance above and below 0.25. So what does this confidence interval mean? Let's interpret it. Well, a 95% confidence interval means that we are 95% confident that the interval from 0.165 to 0.335 captures the true proportion of U.S. adults who watch the TV show. So we're 95% confident that the true proportion of U.S. adults who watch the TV show is somewhere between 16.5% and 33.5%. Is it more likely to be closer to the center of this interval, closer to 0.25, than near the endpoints? No. We cannot say where in the interval, if at all, it lies. We don't know where in the interval P is, if P is even in the interval. We're just 95% confident that it's in the interval. And again, what it means to be 95% confident is that if I took a whole bunch of samples, all of size 100, 95% of them are going to capture P. So only 5% of them are not. So to summarize, the logic of confidence intervals. We take a sample of size n, some size. We obtain a statistic from that sample. Maybe that statistic is a proportion, which we call p hat. Maybe it's a mean, which is x bar. So maybe I'm taking the height of all U.S. adults, and I would average those and find the mean. We use that one statistic from that one sample to estimate the parameter of the population as a whole. One way to estimate it is to form an interval of values in which we think it might lie. The best way we have of forming this interval is to use the statistic that we got from our sample. Since the statistic could be above or below the parameter, we put the statistic in the middle of the interval and go the same distance above and below the statistic. That distance that we go is called the margin of error. That's the error that we're allowing ourselves to have. The size of the margin of error depends on how big we want the interval to be. The larger the interval, the more likely it is to contain the parameter. So a larger margin of error makes higher confidence, which makes a larger interval. Well, higher confidence, that's a good thing. It would be nice to be more confident that my interval contains the value. But in order for that higher confidence, I have to give myself a larger margin of error, which is not a good thing. It means I'm allowing more space, which is the larger interval, and that's not good. Because if I say, well, the true proportion is somewhere between 10 and 80%, that's not very good. That doesn't tell me much. That's not very useful. A larger interval is not as good as a smaller interval. But the payoff is the larger interval makes me more confident. I'm pretty darn confident that it's somewhere between 10% and 80%. Well, that doesn't tell me anywhere where it is in there, and that's not very useful. The smaller the interval, the less likely it is to contain the parameter. So a smaller margin of error, and that's a good thing, is paired with lower confidence. That's not a good thing. But a smaller interval, which is a good thing. Smaller interval means a smaller range of possible values for the parameter. But I've got a smaller interval, that means I'm less confident that it's actually in that interval. The smaller I make my interval, more likely I am to be missing the actual value. So it's a balancing act. To make it more complicated, the margin of error also depends on the size of the sample. The larger the sample, smaller margin of error, and the smaller interval. So a smaller margin of error, that's good. Smaller interval, that's good. But it requires having a larger sample. A larger sample is harder to obtain and more expensive. Smaller sample means larger margin of error and larger interval. Smaller sample is much easier to get and cheaper, but it requires a larger margin of error. That's not a good thing. And gives me a larger interval. Not a good thing. So it's all a balancing act. 95% is usually the confidence level that's used.